Good day everyone and welcome. Today we're delving into a fascinating topic. Track2Act. Predicting point tracks from internet videos enables diverse zero-shot robot manipulation. This groundbreaking research is brought to you by Homanga Bharadwaj, Rusba Mataji, Abhinav Gupta, and Shubham Tulsiani. They've developed a unique model that predicts future point tracks, enabling robots to manipulate objects in unseen scenarios. Stay tuned as we explore how this model outperforms existing methods and opens up new possibilities in the world of robotics. In this slide, we delve into the key highlights of our research. Our primary motivation is to predict future point tracks, essentially capturing the motion of objects between an initial and a goal image. This is a significant step forward in the field of video analysis and robotics. We've also addressed some critical problems that have been plaguing the field. Flow-based methods, for instance, are often too coarse for large nonlinear state changes. They struggle to accurately predict the motion of objects in complex scenes. On the other hand, video-based methods often suffer from issues of implausible generation due to the complexity of the task. Our approach, however, mitigates these issues, providing a more accurate and reliable method for predicting point tracks in videos. This is a significant advancement in the field, opening up new possibilities for video analysis and robotic manipulation tasks. In this slide, we delve into the key insights and contributions of our research. We've discovered that directly predicting future point tracks offers significant benefits. This approach allows us to capture the motion of objects in a scene between an initial and a goal image more accurately than traditional methods. Moreover, our model abstracts out details like appearance and texture, focusing solely on the tracks of a set of points. This simplification makes the task less complex and more manageable, leading to improved prediction accuracy. Our key contribution is the proposal of a single model to predict point tracks. This model is conditioned on three elements: the initial image, the goal image, and a set of points in the initial image. By focusing on these elements, our model can generate accurate predictions for a variety of scenarios. In essence, our research offers a novel and effective approach to track prediction, paving the way for more accurate and efficient motion capture in videos. In this slide, we delve into the key highlights of our approach. The core of our method is a denoising process through a DIT-based diffusion model. This model takes as input a sequence of tokens, each corresponding to a point that we aim to track in a video. The beauty of our approach lies in its flexibility. We train our model using web videos and consider a variable number of initial points that need to be tracked. This allows us to adapt to a wide range of scenarios and tasks. In essence, our model is designed to learn from the complexity and variability of real-world data, making it a robust and versatile tool for track prediction. Moving on to the key highlights of our work, let's first talk about the results. Our model significantly outperforms flow-based and video-based baselines in terms of accuracy. This is a testament to the robustness of our approach. Next, we observed that the predictions made by our model are not only plausible, but also accurately correspond to manipulating the objects as described by the goal images. This shows the model's ability to understand and interpret complex scenarios. Lastly, our model is versatile. It can handle multiple entities or camera movements between the initial and goal images. This flexibility allows it to adapt to a wide range of scenarios, making it a powerful tool for object manipulation tasks. In summary, our model's superior performance, accurate predictions, and versatility make it a promising solution for zero-shot robot manipulation. In this slide, we delve into the key highlights of our work. Firstly, our model, Track2Act, has the ability to generalize to unseen scenes. This means it can adapt to new environments and tasks without prior exposure. Secondly, it successfully realizes the predictions to complete tasks specified by the goal images. This is achieved by leveraging large-scale web video data to learn how objects should be manipulated to satisfy a goal. Lastly, the model's ability to abstract out details simplifies the task of predicting the tracks of a set of points. This abstraction allows us to focus on the essential elements of the task, making the prediction process more efficient and accurate. These highlights underscore the potential of our model in advancing the field of robot manipulation. Let's delve deeper into our solution, Track2Act. As you can see in the figure, it's a pipeline that begins with learning track prediction from web video datasets. This is a crucial step, as it allows us to capture the motion of objects in a scene between an initial and a goal image. This prediction model is trained on a large scale, making it capable of generalizing well to new scenes. Next, we infer rigid transforms of objects based on the predicted tracks in a robot's environment. This is where our system starts to understand how to manipulate objects to achieve a specified goal. Finally, we fine-tune our model with a residual policy learned with limited robot data. This step is essential as it corrects the robot actions derived from the interaction plan, making our system more accurate and reliable. The beauty of Track2Act is that it enables the learning of a single goal, condition policy for diverse tasks, even those unseen before. This makes it a powerful tool for robot manipulation tasks, where understanding and predicting the motion of objects is necessary for successful task completion. Begin a frame. Frame title our solution. Track2Act. Begin a figure, centering, include graphics, width equals 0.8 text width, height equals 0.45 text height, at src, task underscore execution, extracted underscore paper underscore data, 2405.01527v1, figures, 2405.01527v1 figure 1:1.png, caption tiny diverse robot manipulation capabilities enabled by Track2Act. The system learns to predict point tracks from web videos, which are used to infer robot actions in unseen scenarios. End of figure, begin itemize, item Track2Act. A novel framework, begin itemize, item we developed Track2Act, a system that uses web video data to learn how objects should be manipulated to achieve a goal. Item the system combines this with a small amount of robot-specific data to learn corrections over the predicted plans. Item the result is a scalable solution for generalizable real-world manipulation tasks. End itemize, item future directions, begin itemize, item while Track2Act can handle unseen tasks. It currently focuses on short horizon tasks involving a single object. Item future work will aim to extend the framework to handle long horizon tasks involving multiple objects. End itemize, end frame, Let's delve into the heart of our solution, Track2Act. As you can see in this figure, our pipeline involves learning track prediction from web video datasets, inferring rigid transforms of objects based on these predicted tracks in a robot's environment, and fine-tuning with a residual policy learned with limited robot data. This approach enables us to learn a single goal condition policy for diverse tasks, even those unseen before. Now, let's address the limitations of existing approaches. Flow-based methods, while useful, were too coarse to capture large nonlinear state changes between the initial and goal images. On the other hand, video-based methods often suffered from issues of implausible generation due to the complexity of video generation. Our Track2Act system aims to overcome these challenges, providing a more robust and generalizable solution for zero-shot robot manipulation. Moving forward, let's delve into the proposed approach. The authors have ingeniously developed a model that predicts point tracks. This model is unique in its conditioning. It takes into account the initial image, the goal image, and the set of points in the initial image whose future tracks are to be predicted. As you can see in the figure, the Track2Act pipeline is illustrated. It shows the process of learning track prediction from web video datasets, inferring rigid transforms of objects based on the predicted tracks in a robot's environment, and fine-tuning with a residual policy learned with limited robot data. This approach enables the learning of a single goal, condition policy for diverse tasks, even those unseen before. In essence, this model is a powerful tool for predicting how objects should be manipulated in a scene to achieve a specified goal, making it a significant step forward in the field of zero-shot robot manipulation. Moving forward, let's delve into the improvements in our proposed approach. As you can see in the figure, our model, Track2Act, learns track prediction from web video datasets, infers rigid transforms of objects based on the predicted tracks in a robot's environment, and fine-tunes with a residual policy learned with limited robot data. This unique approach enables the learning of a single goal, condition policy for diverse unseen tasks. Now, what sets our model apart? Track2Act abstracts out details about appearance, texture, and so on, to focus on predicting the tracks of a set of points. This simplification not only streamlines the process, but also allows for more accurate predictions. By focusing on the essential elements, our model can effectively predict how objects should be manipulated in a scene to achieve a specified goal. This is a significant step forward in the field of zero-shot robot manipulation. Stay tuned as we delve deeper into the workings of Track2Act in the upcoming slides. Moving on, let's delve into the heart of our system, Track2Act. As you can see in this figure, our pipeline is a three-step process. First, we learn track prediction from a variety of web video datasets. This allows us to understand how objects should move in a scene to achieve a specific goal. Next, we infer the rigid transformations of objects in a robot's environment based on these predicted tracks. Finally, we fine-tune our system with a residual policy learned from limited robot data. This approach enables us to learn a single goal condition policy that can handle a wide variety of tasks, even those it has never seen before. Now, let's talk about our evaluation and results. We tested our model on different datasets and compared it with existing baselines. The results were promising. Our model not only outperformed the baselines in terms of accuracy, but it also showed an impressive ability to handle multiple entities or camera movements between the initial and goal images. This demonstrates the robustness and versatility of our system, Track2Act. Moving on to related works, let's first get an overview of existing approaches in track prediction. There are primarily two methods that have been widely used: flow-based and video-based methods. Flow-based methods are a popular choice in this field. They work by predicting the motion of objects in a scene. However, they have their limitations. One of the main drawbacks is that they are too coarse to capture large nonlinear state changes. This means they often struggle to accurately predict object motion, especially when the scene undergoes significant changes. On the other hand, video-based methods attempt to predict the entire video sequence. However, this approach is often plagued by issues of implausible generation due to the complexity of video generation. In the next slide, we will discuss our approach which aims to overcome these limitations. Stay tuned. Begin a frame. Frame title: a training data and model performance. Begin itemize. Item data sources. Begin itemize. Item 4 diverse web data sources. Epic Kitchens, SMTH v2, Bridge data and RT1 data. Item Epic Kitchens and SMTH v2. Human videos, Bridge data and RT1 data. Robot videos. Item total of 400,000 video clips used for training. End itemize. Item ground truth tracks. Begin itemize. Item code tracker used to obtain ground truth intermediate tracks of points. Item prediction model conditioned on the first and last frames of each video. End itemize. Item model performance. Begin itemize. Item predictions are plausible and correspond to manipulating objects in the scene. Item outperforms flow-based and video-based baselines in accuracy. End itemize. End itemize. End frame. Moving on to the technical details of our research, let's delve into the workings of Track2Act. As you can see in the figure, Track2Act is a pipeline that aims to predict the future motion of objects in a scene. It does this by capturing the movement of specific points between an initial and a goal image. But how does it learn to make these predictions? The answer lies in the combination of two types of data. First, we use large-scale web video data, which provides a rich source of diverse object manipulations. This helps our model learn a wide range of possible movements. Second, we supplement this with a small amount of embodiment-specific data. This data is used to learn residual corrections over the predicted plans. In other words, it helps our model fine-tune its predictions based on the specific characteristics of the robot that will be performing the task. In essence, Track2Act is a blend of broad, general learning from web videos and specific, targeted learning from robot-specific data. This combination allows it to make accurate predictions about how objects should be moved to achieve a given goal. Moving forward, let's delve into the technical details of our approach. As you can see in the figure, our Track2Act pipeline is designed to predict the movement of points in a video frame. This is achieved by treating track prediction as a denoising process, using a DIT-based diffusion model. In this model, the first frame of a video is represented as I0, and the goal, or the last frame, is represented as G. We identify certain points in the initial frame, denoted as P0, that we aim to track. The prediction horizon, or the time frame within which we want to predict the future locations of these points, is represented as H. The future locations of these points in the subsequent time steps are represented as PT. HT equals 1. This forms the basis of our problem formulation and the foundation of our Track2Act pipeline. On this slide, we delve deeper into our approach to the problem. We start by corrupting all points PT by incrementally adding noise, denoted by EK, which represents the diffusion time step. This process leads us to obtain PT and converge to a unit Gaussian distribution N0I. Now, the beauty of this process is that it's reversible. We can generate new samples by reversing the forward diffusion process, essentially moving from Gaussian noise back to the space of point locations. To accomplish this, we train a noise predictor, denoted by V theta, IOGPO. This predictor is key to solving the reverse diffusion process. The figure you see here provides an overview of our Track2Act pipeline, illustrating how these components interact to achieve our goal. In essence, our approach is a dance between adding and removing noise, a process that allows us to predict and track points in a video sequence. Let's delve into the technical details of our proposed research. As you can see in the figure, we present an overview of the Track2Act pipeline. At the heart of our system is a DIT transformer-based architecture designed for V theta. This model is unique in that it conditions not only on the initial and goal images, but also on the diffusion step. This allows us to account for the progression of the video over time. The input to the transformer in each batch is a sequence of tokens, each representing a point specified for tracking. This approach allows us to effectively track multiple points in a video, providing a robust and flexible model for predicting point trajectories. Stay tuned as we delve deeper into the workings of our system in the next slides. Let's delve into the technical details of our research. As you can see in the figure, our Track2Act pipeline is a comprehensive process. A key component of this pipeline is the training of our prediction model. We use web videos as our training data, considering a variable number of initial points that need to be tracked. This allows us to adapt to different scenarios at test time, where any set of points in the initial image can be specified. We've designed our model to be flexible and robust. We don't make any assumptions about the objects to be tracked or the camera motions in the videos. Furthermore, we don't curate the training videos in any specific way, apart from ensuring they are of 4 to 5 second duration. This approach allows us to train our model in a wide variety of situations, enhancing its ability to predict and track effectively. In essence, our model is trained to handle the unpredictability and diversity of real-world scenarios, making it a powerful tool for object manipulation tasks. On this slide, we delve deeper into the technical aspects of our proposed research, Track2Act. As you can see in the figure, it provides an overview of the Track2Act pipeline. Now, let's talk about how this model improves upon previous approaches. Firstly, it abstracts out details such as appearance and texture, focusing instead on predicting the tracks of a set of points. This allows for a more streamlined and efficient process. Secondly, it can handle multiple entities, such as a human and an object, or a robot and an object. It can also manage camera movements between the initial and goal images. Lastly, the model's predictions are not just theoretical. They are plausible and correspond to manipulating the objects in the scene as described by the goal images. This makes Track2Act a practical and applicable tool in the field of robot manipulation. As you can see in the figure, our Track2Act pipeline is designed to leverage diverse video data for real-world manipulation tasks. We've evaluated our model on a variety of datasets, including Epic Kitchens, SMTH, SMTH v2, bridge data, and RT1 data. These datasets provide a wide range of scenarios, from everyday activities to specific robot tasks, allowing us to test the versatility of our model. We use a metric, denoted as increment, for quantitative comparisons. This metric ranges from 0 to 1, with higher values indicating better performance. We'll also be presenting qualitative results, which include visualizations of our track predictions and robot evaluations. These visualizations will give you a clearer picture of how our model performs in real-world scenarios. In essence, our experimental design is aimed at thoroughly testing our model's ability to generalize across different tasks and environments, and to provide you with a comprehensive understanding of its performance. Moving on to our technical results, let's take a look at this figure. It showcases visualizations of point track predictions for different tasks, followed by closed-loop execution with the residual policy. As you can see, the predictions are plausible, and the robot execution successfully realizes these predictions to complete the tasks specified by the goal images. Now, let's delve into some key results. our model outperforms flow-based and video-based baselines in terms of accuracy. The predictions made by the model are not only plausible, but also correspond to manipulating the objects in the scene as described by the goal images. What's more, our model can handle multiple entities, such as a human and object or robot and object, or even camera movements between the initial and goal images. We've evaluated our model on different datasets, including Epic Kitchen's SMTH-SMTH-V2, bridge data, and RT1 data, demonstrating its versatility and robustness. Interestingly, our model's ability to abstract out details about appearance, texture, etc., simplifies the task of predicting the tracks of a set of points. This feature allows the model to generalize to unseen scenes and successfully realize the predictions to complete the tasks specified by the goal images. In essence, our model is not only accurate but also versatile, robust, and capable of generalizing to unseen scenarios. Moving on to our technical results, let's take a look at this figure. It showcases visualizations of point track predictions for different tasks, followed by closed-loop execution with the residual policy. As you can see, the predictions are plausible, and the robot execution successfully realizes these predictions to complete the respective tasks specified by the goal images. The generalization level for each task is also shown. Now, let's delve into the implications of these results. Firstly, our results suggest that directly predicting future point tracks is beneficial for capturing the motion of objects in the scene. Secondly, the model's ability to handle multiple entities or camera movements indicates its potential for complex scene understanding and manipulation tasks. Thirdly, the model's performance across different datasets indicates its robustness and generalizability. Lastly, the model's ability to abstract out details about appearance, texture, etc. indicates a novel approach to simplifying the task of predicting the tracks of a set of points. This is a significant step forward in the field of robot manipulation and scene understanding. Begin a frame title future directions and challenges, begin itemize, item expanding scope of tasks, begin itemize, item, while Track2Act has shown promise in manipulating single objects in short horizon tasks, it would be interesting to extend this framework to handle long horizon tasks involving multiple objects. End itemize, item enhancing the residual policy, begin itemize, item. The current residual policy model is a transformer based on the DIT architecture. Future work could explore other architectures or learning strategies to further improve performance. End itemize, item leveraging more web data, begin itemize, item. The potential of scalably leveraging web data for object manipulation prediction is vast. Future research could explore more sophisticated methods to extract and utilize this data. End itemize, end-iframe,